Can you hear us, Aeryeong?
Yes, I can hear you.
Yes.
Yes.
But we could just before. Can you,
How about now?
we cannot hear you. But, yeah, but we need it already. Aeryeong, can you?
Yes.
Yes, it's perfect. Now we can hear you.
Okay.
Yeah. So, can everybody hear? Yes, okay, thank you. So the next speaker is Aeryeong Seo from Kyungpook National University. I hope I spelled it well. So it's really a pleasure to have you. And the title of the talk is Symmetric Differentials and L2 Holomorphic Functions.
First of all, thank you very much for to organizers for giving me this opportunity to speak in this conference. And I'm very sorry that I could not attend there at present. I hope later, if I have chance, I can join there. Today, I'm going to talk about symmetric differentials over complex hyperbolic space and L2 holomorphic functions on some the unipole fiber bundles. This is a co-work with Seung-jae Lee in IBS. Let me introduce the hyperconvexity of complex manifold. Here, let X be a complex manifold. And we are going to say this X is hyperconvex if there exists a bounded plurisubharmonic exhaustion on it. That means there exists a continuous function phi from the manifold to negative numbers such that dd bar phi should be semi-positive. And for any negative constant c, the sub-level set should be relatively compact in X. And we are going to say X is weakly one complete or pseudo-convex if there exists the C infinity plurisubharmonic exhaustion function. It is well known that any hyperconvex manifold should be weakly one complete. But actually the converse is not true. The counterexample was given by Herbert in 1998, and the counterexample domain is given by like this. And I want to introduce some nice properties of hyperbolic manifolds, hyperconvex manifolds. Here is the properties of weakly one complete complex manifolds. Here, let X be a complex manifold of dimension n. Then there are several cohomology vanishing theorems. I would like to introduce just these three. Here is a type, I'm sorry. Nakano showed that for any positive line bundle over M, if we suppose M is weakly one complete, then HPQME should vanish for any PQ if P plus Q is greater than N. And in case of vector bundle over M, if we assume weakly one complete condition and some Nakano positivity or negativity condition, then there are some vanishing theorems. If the manifold is a domain in complex Euclidean space with real analytic smooth boundary, then Grauerit showed that omega admits a complete Kähler metric if and only if omega is pseudo-convex. And as Professor Ebenfeld commented, a bounded domain in Cn is pseudo-convex if and only if it admits a complete Kähler-Einstein metric. If the complex manifold is hyperconvex, then there are better properties. For example, in 2004, Chen showed that Bergman metric of hyperconvex manifold is complete. And very recently, Ozawa showed that if the domain is hyperconvex, then the Bergman kernel diverges to infinity if the point tends to the boundary. Here are some examples of hyperconvex manifolds. So Diderich and Fornes showed that any bounded pseudo-convex domains with C2 boundaries should be hyperconvex. And later, Kessman and Rosé reduced the regularity of the boundary to C1. And Ozawa Shibuni showed that any pseudo-convex domains with C2 boundaries in complex projective spaces should be hyperconvex. And bounded homogeneous domains are also hyperconvex. And recently, Deng and Fornes gave several fiber bundles over complex manifold, which are hyperconvex with interesting properties. One of them, one of the interesting example to me of Deng and Fornes is the following. So there exists a disk fiber bundle over Hof manifold, which does not admit any non-constant holomorphic functions. So it is well known that Hof manifold is not a Kähler. So here is my question. So if the base manifold is a compact Kähler manifold, and if the fiber is bounded symmetric domain, then whether there exists a non-constant holomorphic function. And Seung-jae Lee and I studied about this for a simplest case. Let me introduce the unipole fiber bundle. So here Bn is the unipole of dimension n. And there exists an embedding from Bn to Cpn given by G1 to Gn to 1, G1, Gn. And this is respect to the homogeneous coordinate of Cpn. Then automorphism of the unipole is SUN1, and automorphism of the projective space is the projectivized general linear group. And actually, if we embed the ball into Cpn, then the image is nothing but the complex lines which are negative definite with respect to bilinear form, non-degenerate bilinear form with the signature N1. So the automorphism of En is the linear map preserving that non-degenerate form. So it is SUN1, and any automorphism can be extended as an automorphism of the projective space. So now we are going to consider a complex hyperbolic space form, that is, sigma is the Born quotient by gamma, where this gamma is a discrete torsion-free subgroup of automorphism group. And then we are going to define this omega to be the quotient of Bn times Bn with respect to the diagonal action given by this. Then this omega is a holomorphic Bn fiber bundle over a complex hyperbolic space. So inside of this omega, there is just a compact scalar manifold, which is biholomorphic to sigma. And actually, it is a diagonal of Bn times Bn. Because, as I told you before, any automorphism can be extended to the automorphism of CPN. So we can consider the following CPN fiber bundle. And this omega is an open subset in this bundle. And now consider the following function, delta, from Bn times Bn to R, given by like this. As you see here, 1 minus G modulo square is the defined function of the unit ball. And this delta is invariant with respect to the diagonal action. That is because each term can be expressed by the Bergman kernel of the unit ball. And because of the transformation formula for biholomorphisms, then we can show easily that this delta is invariant. And another property of this omega is hyperconvex. So more precisely, this delta defines a plurisubharmonic exhaustion function. Here, if R is less than or equal to 1/2, then it is plurisubharmonic. And actually, the Diderot-Hornets index of this domain is 1/2. And here are some remarks. If we consider the bounded symmetric domain, then what I said before is also true. So here, a bounded domain omega is symmetric if for any point P in omega, there exists the automorphism. So involution such that it has P as an isolated fixed point. So, and these bounded symmetric domains are classified in 1920s by Cartan, and these are the product of the following irreducible ones. So here, the first 4 are classical and last 2 are exceptional. So I'm sorry for the notation. If we let this omega to be a bounded symmetric domain, then we can show that the quotient of omega times omega by gamma with respect to the diagonal action is also hyperconvex. Actually, in the previous formula, instead of this defining function, if we put the generic norm of bounded symmetric domains, then we can show that that is hyperconvex. And the second remark is, if we consider the case product of omega, like this. And then we take the quotient by diagonal action given by like this. Then it is also hyperconvex. In this case, this manifold is omega k minus 1 fiber bundle over omega mod gamma. So let's go back to the previous question. And we are going to assume that n equal to 1. So omega is given by this with the unit disk, and the gamma is a subgroup of SU11. Then in this case, Ozawa observed that this Poincare series with n is greater than or equal to 2 defines a holomorphic function on omega. And with this observation, in 2017, Adachi explores an explicit system of functions that generate the set of holomorphic functions. So here we give a inner product given by like this with the weight, and we can define the weighted L2 spaces like this. And then weighted Bergman space is the intersection of the set of holomorphic function and weighted L2 spaces. Then his result is this for canonical line bundle K sigma, and this sigma is a Riemann surface. Then he constructed an injective linear map from the holomorphic section to the canonical line tensor power of canonical line bundle to the set of holomorphic function. And this map has a dense image in here with compact open topology. And actually he could express explicitly what is the map, what is the form of this map. And it is given by like this. And Seung-jae Lee and I tried to generalize Adachi's result to higher dimension. So instead of this canonical line bundle, we should consider the symmetric bundle of the cotangent bundle. Here, let X be a complex manifold. And we're going to denote this SM TX star to be M's symmetric power of the cotangent bundle of X. And it is called the holomorphic section of this bundle is M's symmetric differential of X. And now consider the complex hyperbolic space and omega constructed, induced from that. Then we could also construct an injective linear map from the set of symmetric differential to the set of holomorphic function. And actually it also has a dense image in this set with compact open topology. To prove, to construct this map, we need to consider the following raising operator. So here, let's consider a map tau from smooth section to the smooth section of this bundle. Then we can define a raising operator with respect to this tau from this to here. So the power of symmetric bundle raised by P, and there is a 0Q form part given by like if we put for smooth section U, if we express tau U like this, where here E bar Q is a PQ part, and this is a symmetric part, then we just take the symmetric product with holomorphic form part to here. Then we can get the raising operator. Here are some examples. The first one is if we let G be the scalar metric on X, and this capital G is its scalar form, and let's consider this E1 to En to be local frame of the cotangent bundle, so that G can be expressed by this. So that means this is also normal frame. Then corresponding raising operator is given by like this. So we just take symmetric product with EL and take some like this. Second example is like this. If we consider the turn curvature of the scalar metric, then the curvature tensor is given by like this with respect to the induced metric on the cotangent symmetric power of the cotangent bundle. Then if we denote the local, if we denote the curvature tensor in terms of local coordinate and the frame, then raising operator with respect to this curvature form is given by like this too. So here is a sketch of the proof. At first, we need to consider some special automorphism of the uniform. So here, fix a point Z in Bn, and then we are going to define this Tz like this. Here, Pz is a projection to the line generated by this G, and this Qz is also the projection to the orthogonal complement of the line generated by this G. Here are some nice properties of this automorphism. The first one is this Tz is an involution. So if we compose Tz, then it is an identity. And if we put this TZW in the defining function of the uniform, then we can get the delta function. And minus low delta is a pluri-subharmonic exertion on Bn times Bn, which is strictly pluri-subharmonic of the diagonal and invariant under the diagonal action. So with this automorphism, we are going to take very special orthonormal frame given by this. Let's consider the differential of Tz and evaluate this at Z. Then using the global coordinate of the uniform, we can have the matrix And then we define EJ, which is EJ by like this. Then we can show that this EJ gives an also normal frame of the cotangent bond with respect to the Bergman metric. And next, we are going to consider the symmetric differential. If we express this symmetric differential with respect to the orthonormal frame defined just before, and we are going to define the formal sum F like this. So we change this E to EZW. Then actually, because the transformation formula of this TZW with respect to the automorphism is the same of the transformation formula of this EJ. So because of that, this F should be gamma invariant. Of course, it should be like with respect to the diagonal action. But unfortunately, this FL is holomorphic with respect to W, but it is not holomorphic in G variable because of this part. So we want to make this holomorphic. So to make it holomorphic, we will find a sequence with a smooth section such that if we take the infinity sum, then it is holomorphic. The necessary condition to make this F holomorphic is the following recursive D-bar equation. So if we choose else symmetric differential, then we take phi k to be 0 if k is less than L, and we put phi L to be this symmetric differential. And if m is greater than or equal to m, then we are going to put phi L plus m to be the L2 minimal solution of the following given. So if we put the section phi L plus m should be the solution of the following D-bar equation, where this RG is the raising operator, where G is the scalar form of the induced metric from the Bergman metric. Actually, we can show that this is sufficient condition. So now what we should do is the following three things. The first one is we should show that there exists the D-bar solution of the above equation here. By using induction, actually we could show that this RG phi L plus m minus 1 is D-bar closed. And if we use Hardy theory, then we can show that there exists a solution. And next step is we should show that the following formal sum converges. To do that, we should use the following. We should use the following equations. So for general complex manifold, we can prove that the commutator of this Laplacian and raising operator should be the raising operator with respect to the Chern curvature. And then if we use that the ball has a constant holomorphic sectional curvature, then we can show this raising operator with respect to the curvature should be equal to 2m RGU. After that, we use this equation recursively to get this norm of phi n plus m. It looks a bit complicated, but we can show that this formal sum converges. And then last step is to prove this F is actually holomorphic. On the other hand, so what I said until now is if there exists a symmetric differential, then we can construct the holomorphic function. Then we can ask the converse way. For example, here we could show that there exists a map from the set of holomorphic function to the symmetric differentials. And if this F vanishes on the diagonal up to case order, and if this F does not vanish on k plus 1's order, then the image should be a symmetric differential of degree k plus 1. In particular, as Oda observed, we could observe that there is a Poincare series on Bn times Bn, such that if this capital N is greater than or equal to n plus 1, then this should converge. So that means if gamma is the discrete subgroup of the automorphism group of the unit ball, and if this n is greater than or equal to n plus 2, then there exists a symmetric differential of degree n. And I want to comment about the existence of symmetric differentials. Actually, this corollary is already known. I think it is already known for expertise, because if we use Nakano positivity of symmetric bundles of cotangent bundle, then the symmetric differential exists. Actually, if we take the n plus 2 symmetric bundle, then it is Nakano positive. With the smaller degree, it is not. Then why the symmetric differential is important is the following. Like Kobayashi showed that if X is a compact complex space with ample cotangent bundle, that means there are a lot of symmetric differentials, then this X is Kobayashi hyperbolic. And in 2012, these three people showed that if X is a compact scalar manifold, and if there is a finite dimensional representation of the fundamental group over some field with infinity image, then this X has a non-zero symmetric differential. And here is the following question of Kringler. So if he asked that what is the minimum number for the given complex manifold which has the symmetric differential. So actually I wanted to reduce the degree to less than n+1, but actually this Poincare series is the best we could obtain. Like if we can obtain the Poincare series with less vanishing order, then maybe we can get the lower degree symmetric differential. Here is a small, actually our case, Bn times Bn mod gamma is very special. So we tried to generalize that theory to another case, but here is a very small generalization. Consider this M. M is a compact Kähler manifold of dimension n. Let this M tilde to be its universal covering. And then put this gamma, the fundamental group of M. Then M should be biholomorphic to this. And suppose that there is a homomorphism from the fundamental group to automorphism. And also suppose that there exists an embedding from the universal cover to Bn, which is low equivariant holomorphic isometric. So that means for any gamma and z, it should satisfy these equations, equalities. So that means this compact Kähler manifold should be holomorphic isometrically embedded into this Ball quotient. So in this case, we consider this Bn fiber bundle, which is given by M tilde product MPn, and we take the quotient with the relation given by this. Then if we take pullback of the symmetric power of tangent bundle of this sigma to M, we can show that there exists L2 holomorphic function on this domain. Like in this case, M tilde, in this case, here Ball quotient does not necessarily to be compact. Thank you very much for your attention. And I'm sorry it was too short.
Thank you very much. So, are there some questions? Maybe we start with the people online. Oh, Gotan, please.
Well, no questions for the moment.
Oh, I thought you raised the hand. Sorry. Yeah, you clapped. Okay, very good. Are there some questions in the audience? Maybe I have a question. You considered quotients of the ball, start with, right?
Yes.
Can you hear me again?
I can hear you.
Yes. And so is it possible to change the ball with another domain for which we can consider a discrete group of automorphisms? And because it seems there is a role played by the Keller metric you consider.
Yes.
And in the case of the ball, you can consider the Bergman metric or the Keller-Einstein metric, but we could imagine, depending if we change the domain, that we may change, we may consider different Keller metrics, right?
Yes, yes.
What is the effect?
Like if we can find the automorphism, like canonical automorphism, like TZ, and if we can control the curvature, then it is possible. So, for example, in case of bounded symmetric domain, but
we controlling the curvature, what does it mean exactly? The fact that it's bounded?
So in case of the unipole, we use the constant holomorphic
Right.
sectional curvature condition. So that makes many calculations very easy. But in case of other case, I have no idea how to deal with it.
Okay. And
Maybe,
even which metric to consider, right?
yes, yes. Maybe we should consider some distribution which has the constant curvature, and then it is maybe possible.
Okay. Okay, thank you. Filippo?
Okay, so first of all, Aeryeong, many thanks for your talk. I have, it's mostly a curiosity. You know that in hyperconvex domain, you can define the pluricomplex green function, the one defined by Klimek, and then the Maillet show that it exists, and I think it's continuous if it's just hyperconvex and continuous. So I'm asking if you know whether using the other structure you consider, you can get information on the pluricomplex green function in your case.
Sorry,
Okay.
I couldn't.
Oh, you.
Sorry.
Just a second.
Would you say once more? I couldn't understand.
Filippo, I think you are muted.
Can you hear me now? It's better?
Yeah.
Okay, so my question was about whether you can get information on the pluricomplex green function. If you have a hyperconvex domain, you can define, and I think the Maillet showed that it's continuous. And so I'm asking whether with your additional hypothesis and structure, you can say something more like regularity or some behavior.
Oh, I see. Oh, sorry. Oh, I have no idea.
Okay, no problem. It was just a curiosity, as I mentioned before. Thank you anyway.
Thank you for asking.
Thank you very much, Aeryeong. So that's the end for this morning session, right? And we'll start back at 2:30 precisely. Okay. Thank you very much. See you later.